So one of the things we saw in the design of FIR filters by windowing was that as you increase the length of the rectangular window, the transition width of your designed filter goes down. It's inversely proportional to the length of the filter. But the other thing we realized was no matter how much is the width of how much is the length of the filter, it does not decrease the size of ripples in the pass or the stop band. Okay? So if your original filter that you were working with, if your original filter had, you wanted a cutoff at omega c, we saw that as you so this is what the effect of windowing is. Right? There is a transition width which is not sharp, and then there are ripples. Now as you increase the length of the filter, this transition width decreases. So you maybe get this. So the transition width can decrease, but one of the things we realized was that the ripples, the size of the ripples, that stays consistent regardless of how much is the length of your filter, or accordingly how much is the length of the rectangular window. So the question we are interested in addressing in this lecture is, how can we achieve more attenuation in the stop or pass band? Okay. So we effectively want, when we talk about the window, we want a smaller peak side lobe height, relative peak side lobe height, or when we talk about the delta, the ripple size, we want the delta to be smaller. Well, the way to do that is change the rectangular window into something that transitions more smoothly from 1 to 0. And also 0 to 1. Okay, so your rectangular window, if you recall, it's simply 1 everywhere. So that's n minus 1. So this is your rectangular window, and in most window-based designs, what is the size of your ripple, or what is the size of your peak side lobe height, which is, when we look at the Fourier transform of that, just the magnitude, we get this kind of Fourier transform from minus pi to pi, and the peak, relative peak side lobe height, which is the height of the peak side lobe divided by the main lobe, that stays constant regardless of the length of the rectangular window. And the reason for that is, well, it will stay constant for all windows, but in this case the relative height is 13.3 dBs. So the side lobe is 13.3 dBs below the main lobe, and the question is, if you want to increase that, what should we do? And the way to do that is, instead of going very sharply, you were all zeros and you went very sharply to 1, or you were all ones and then you went sharply, abruptly to 0, let's make that transition a little smoother. So Based upon that, people came up with many different types of windows that you can use beyond the rectangular window, where the process is still the same. You start with an infinite length filter, you multiply it with a finite length window to get a finite length filter, but the window, instead of this rectangular shape, has a shape that transitions more smoothly from 0 to 1 and 1 to 0. So we are going to look at some of those windows. So the first one is called the Bartlett window, also known as the triangular window. So these windows were proposed by different people, and they were given the names based upon the person who proposed them. So a Bartlett window is one minus absolute value of n divided by m plus 1. Minus m less than or equal to n less than or equal to m. So if you remember, we were defining n equal to 2m plus 1. This is, the windows are described symmetric around 0, and of course if you want to make them causal, you just shift them by an amount m. So compared to the rectangular window, if you compare that, Bartlett window basically looks like that. It starts from 1, then slowly ramps up. Let's call this minus m. It slowly ramps up to 1, and then it ramps down. It's supposed to be symmetric. I didn't do a very good job of making it symmetric, but the idea is it's just like taking samples of a triangle. So if you have a triangle, you just take samples of that triangle and that's your window. So the length is still goes up to m, the length is still n equal to 2m plus 1, but the window now is slowly transitioning from 0 to 1 and 1 to 0. Okay. And we'll look at what happens when you go from rectangular window to Bartlett window or triangular window. There are other 3 major types of windows that were proposed by different people. The next one was called Hahn window, which is 1/2 1 plus cosine of pi n over m minus m. The next one is Hamming window. So Hamming and Hahn are very similar. The difference is what kind of coefficients are used. 0.54 per 0.46 cosine of pi n over m. If you compare the two, you see that effectively Hahn is using both the coefficients are 0.5, whereas Hamming is using 0.54 plus 0.46. Okay. And the last one of the fixed windows, we'll look at the case where the windows can be more arbitrary, is Blackman window, which is 0.42 plus 0.5 cosine of pi n over m plus 0.08 cosine of 2 pi n over m. All these windows I'm describing as symmetric around 0. Of course, when you want to design causal filters, you will just shift them by m and multiply with your final filter that you want to approximate. Okay, so here is a depiction of the different types of windows that you see. This is their shape. This figure is only showing you the window in terms of a continuous form. What you really get is you just take samples of that window, okay? And this is taken from Oppenheim and Schaefer, where the notation is different. So you should really think of this as this m should be really n. Okay? So okay. So if you look at it, basically this straight line is the rectangular window, which is that you are just taking samples of this. That's your rectangular window, stays 1 all the time. Then the Bartlett window, which is this triangle. And then if you look at the Hahn and the Hamming window, they look very similar to each other except a little bit of a change. So because of the coefficients that they have used, and so Hamming is this dark line, okay, and Hahn is this dashed line. So you see that basically up to this point, both Hamming and Hahn are almost the same because their coefficients are very similar to each other. And the major difference is basically how they end up at the very edges, okay? Hamming still has a sharp transition. So Hamming from here, this endpoint, it still goes to 0, but it goes to 0 from a very small value, whereas Hahn, it smoothly goes to 0. Okay. And then the Blackman window, which is this is the Blackman window. Okay. Of course, they are based upon these sinusoids, so they have this shape. So what's the purpose of these different windows? What role do they play? It turns out that as you change different windows, so many of these windows have a much smaller relative peak side lobe height. And as we talked about earlier, peak side lobe height means if you have a smaller peak side lobe height, then that means that the amount of ripples that you get in your pass and stop bands are going to be smaller. Okay? So you can really have smaller ripples using these windows. And what's the relationship of those different things? Well, here is the relationship. We talked about it earlier that, so rectangular window we have already studied. These are the results we had gotten for rectangular window. Okay. The peak side lobe height, the ASL, we had written that. For rectangular, that's minus 13 dBs, and because of that, the maximum ripple size, because ripples are not uniform, the maximum ripple size is minus 21 dBs. Now, as you go to Bartlett, so as you go to Bartlett, you see that your peak side lobe amplitude now goes from minus 13 to minus 25 dBs. Okay? And it is going to stay that way no matter what the length of your window or of your filter is. And the approximation error for Bartlett is also minus 25 dBs. On the other hand, if you go to Hahn, that's minus 31 and minus 44 in terms of approximation error. Hamming even does better. It's minus 41 dBs and minus 53 dBs. And then Blackman has the highest attenuation. It's minus 57 dBs for the peak side lobe height and minus 74 dBs for the ripple size. Right? So, and the question is then, why should we just not pick the Blackman window? Why should we stick with the rectangular window or any other window? Because we see that the peak side lobe amplitude or the approximation error of the Blackman window is the highest. So we get the smallest ripple when we are working with Blackman window. Why should we pick any other window? And the answer is that we have to worry about the transition width, which is a function of the main lobe width of the window. Okay? So as you go to different windows, you get more and more and more attenuation. But what happens is that these windows, the transition width or the width of the main lobe actually increases. So it turns out, compared to the rectangular window, all these windows have very small peak side lobe heights, which means that the maximum size of ripples in the pass and stop band is smaller than the rectangular window. But what happens is that as the peak side lobe height goes down, there is always a compromise. There is no free lunch. And when you decrease the peak side lobe height, what happens is that the main lobe width of these windows increases. And we know that the main lobe width is proportional to the transition width of your eventual filter. So the transition width of the final filter increases. So the compromise is that as you increase the side lobe, this implies that the main lobe width goes up. Okay? Now, while this is a compromise, you can always counter that, because remember, no matter what we do with the length of the window or length of the filter, you cannot change the side lobe height, the relative side lobe height with the length. But you can always change the main lobe width with the length of the filter. Okay? So that's why those other windows are still helpful. So if we compare the main lobe height, the main lobe width versus the side lobe height, we see that rectangular window, again this should be simply n. Just replace all the m's by n. So when we go from rectangular to Bartlett window, we get a gain. We really need to focus on the ripple size. Let's not worry about the peak side lobe height that much. So if we focus on the ripple size, we change the attenuation by 4 dBs. But when we do that, we see that Bartlett window delta ml is equal to 2 times rectangular delta ml. What it means is that if you compare the two, for the same amount of transition width, if you are using the Bartlett window, you need twice the length of the filter. Okay. And the gain you get is, by using the Bartlett window, that your attenuation is much smaller. Now you go to Hahn, the attenuation goes to 44 dBs. So you have an advantage of 23 dBs better attenuation, and the width or the transition is still a factor of 2 loss in transition width. Okay. So actually the main lobe width of both Bartlett and Hahn are exactly the same. So it turns out that actually Hahn is just better than Bartlett. There is no reason for you to use the triangular window. Let's come to Hamming, and you see that attenuation of Hamming is 32 dB is better than rectangular, and it is still only factor of 2 loss in transition width compared to rectangular. So it turns out that even when you talk about Bartlett, Hahn, and Hamming, there is no reason to use Bartlett and Hahn at all. All you should do is either use rectangular or Hamming window, because the rest of the two windows, they have smaller attenuation but the same main lobe width. Okay. And then the final one is Blackman, which gives you the most attenuation in your ripple size. That's 53 dBs lower than rectangular window, and you have a factor of 3 loss in transition width. Okay. So in window design, you often hear people talking about Hamming window, because that's sort of like a good compromise between transition width and attenuation. 53 dBs is a big attenuation. But if you really need, you can go to Blackman, and then you have to pay a price of factor of 3. Okay. So compared to when we are talking about window-based filter design, the idea is basically you start with an infinite length filter, and then you figure out which one of these windows will satisfy your needs for the ripple size. Okay. So if we talk about practical design of FIR filters, remember what we will be given is someone will say that the transition width will be given. Typically that is given in terms of factors omega p, which is the pass band, and omega s, the stop band. Where does the pass band should end and where does the stop band should begin? Okay? And the second thing you will be given is maximum ripple size. In stop/pass band delta. So for window-based methods, in general, we talked about it in the last lecture, that you can be given the ripple size in the pass band and the ripple size in the stop band, but for FIR filters by window method, the two are equivalent. Okay? So someone will say, here are the criteria. What I want is that up to omega p, instead of 1, I want you to be within 1 plus delta and 1 minus delta, and then up to from omega s to pi, I want you to be within delta. Okay? So the way you do that is, first of all, because we know that the attenuation is not a function of the length of the filter. So based upon what is your delta requirement, based upon the size of the ripple, so we start with delta and pick the window that gives us delta value smaller than the required delta. Okay. So if someone said, I want the ripples to be no bigger than, let's say, 15 dBs, so you want attenuation to be at least 15 dBs, then we know that a rectangular window is good enough. So if my given delta is 15 or 20, I can use the rectangular window. But if someone says my required delta is, let's say, 40 dBs, I want the attenuation to be 40 dBs. Then which window should we pick? So you could pick either Hahn or Hamming because they both satisfy the delta requirement. But then the issue is, why pick Hahn? Because the transition width of that window is the same as Hamming, and Hamming is giving you more attenuation. So even though someone said, I only want a 40 dB attenuation, if you can get 53 dB attenuation, there is nothing wrong with that. But you cannot pick rectangular window, because the attenuation given by rectangular window is only 21 dB. You can even pick Blackman window, that's fine, because even Blackman window is giving you more attenuation. So an attenuation more than what you need is fine, but you can't have less than that. Similarly, if someone said, I want an attenuation of 50 dBs, then you can either pick Hamming window or Blackman window. If someone says, I want attenuation of 70 dBs, then your only choice is Blackman window. And if someone wants attenuation of 80 dBs, then none of these windows will work. Okay? So once we figure out which window we want, so we fix the window shape. Okay? And now our goal is find the length of the window which determines the length of the filter. Okay. And how do we determine the length of the window or length of the filter? That is then a function of the transition width. So the transition width which is defined as, in this case, omega s minus omega p, that is proportional to the main lobe width. Okay. So what you try to do is, once you have fixed the window, you try to find out the value of m that will give you the required transition width. And that's how you figure out the length of your filter. And in general, if you go back to the table that we looked at, because for the same transition width, Blackman window is going to require a bigger value of m than Hamming window, then you are better off, if Hamming window satisfies your attenuation needs, then you are better off working with Hamming window than Blackman window. Similarly, if rectangular window satisfies your transition needs, then you are better off working with rectangular window than any other window. Okay? And so using the table that we saw before, for fixed omega p and omega s, the relationship is that if n is the length of a filter using rectangular window, then 2n is the length that you need so 2n is the length that we need for Hamming window, and 3n is the length that we need for Blackman window. Okay. So we'll go back to the FDA tool in MATLAB to try to look at whatever we discussed in terms of the role of different windows. So let's start with the low pass filter. Again, we are doing FIR filter. We are looking at window based method, and if you do that, then you get different types of windows. We have of course discussed only a few types of windows. So we have talked about rectangular, triangular, Hahn, Hamming, and Blackman. Right? There are all these other types that we are not going to talk about. So let's first say we fix the length of the window. Right? So we are going to work with a length 10 window, which is the length 10 filter. And we want a cutoff of pi by 4. And let's start with rectangular. So if we do that, we design the filter, and we look at that. Of course, we have the length of the filter is only 11. So even though we wanted a cutoff of 0.25, it goes to 0 at a very slower pace, and this side lobe, this ripple size is about minus 20.9 dBs. So now just let's change this to Hamming. If we change this to Hamming, what do we suspect will happen to this frequency, this magnitude response? I'm gonna cheat. I want to be sure I say the right thing. 53. Okay, because it didn't seem like 57. So what will happen if I change it to Blackman window? Yeah?
Same thing as before, you're just going to get more attenuation, and the transition width is going to be increased by a factor of 3 instead of...
Yeah. So the transition width and the attenuation will be, let me cheat again, 74 dBs. Any questions? One question that comes up at this point is what happens, because if you go to Hamming, so we have now talked about 3 main windows, rectangular, Hamming, Blackman. So what if you want attenuation either somewhere in between? The only option is you go directly from rectangular to Hamming. What if you want attenuation somewhere in between and you don't want to use twice the factor to increase, you don't want to increase the length of your filter by a factor of 2? Or what if you want attenuation even perhaps bigger than Blackman? What if you want anything in between of these 3 main windows? So for that, what we have is adjustable windows. So all these windows are fixed in the sense that their shape is fixed. Adjustable windows are windows that change shape to obtain a desired attenuation of the peak side lobe or the desired attenuation of your ripples. Okay. Now, by definition, since you are changing the shape of these windows are going to be functions of at least one more parameter. So the 2 most common windows that are used are the first one is called Dolf-Chebyshev window. I'm not going to write down the analytical formulas for that because they are really sort of messy and you can just use MATLAB to generate them anyways. In this window, the extra parameter is the side lobe, relative side lobe height in dBs or linear scale. Okay. And the second one is what's called the Kaiser window, which is perhaps more frequently used than Dolch-Chebyshev window. And the extra parameter in that, so one parameter, of course, for any window is the length of the window. The extra parameter in Chebyshev window is a number called beta. Okay. And using these parameters, you can actually design any desired filter with the required length. So again, if you go back and look at the tool, you can select the Kaiser window, and the moment you select the Kaiser window, an additional option opens up, which is what beta do you want? Okay, this is the option where you specify the order and you select the beta. Another option for an automatic design is actually you just say that I want, you specify the omega p, the passband frequency, so you say it's supposed to be 0.2 and 0.3, okay? And then you specify how much attenuation you want in your stop band, how much ripple size you want in your stop band. So that's 80, and you select minimum order. It's automatically going to generate a filter with it is automatically going to generate a window with the desired beta. So you do that, and it's going to generate such that in the stop band you have 80 dBs attenuation. Right? And if you look at it, it is giving you an order 101 filter. It has length 102, which is listed here. If I drop this to, let's say, 50 dBs, and I again use the Kaiser window, I just press that, and now it keeps the transition width the same, and it has actually reduced the length of my filter to 60. So automatically it gives you the right length filter that achieves whatever you are interested in. Okay. If you know more about how to select the beta, then you can really specify the order and play with different values of beta to come up with a window that satisfies your needs. Okay. And of course, you can always go and play with the impulse response. So remember, a low pass filter, right, is nothing. The ideal low pass filter has an impulse response which is a sink. When you are windowing, you are cutting off left and right parts of that sink, but also you are multiplying it with different values in between. So as I change different values of beta, you are changing the shape of your filter. And that is giving, so beta is 0.2, it's 0.1, can do 0.6. There are these minute changes in the shape of your filter which are creating changes in how your end filter, how the magnitude response of your filter looks like. Okay? And of course, all of these designs, the desirable property is that all of these FIR filter designs are also giving you linear phase causal FIR filters. Okay? Now you can design IIR filters. The advantage of IIR filters over FIR filters is that you can actually use much less resources to achieve the same attenuation, the same passband. The major challenge in IIR filters is that you cannot achieve the linear phase. I'll conclude by pointing out that there are other types of, there are other means of designing of designing FIR filters beyond the window method. Some of those techniques effectively use computational algorithms to recursively generate a filter that satisfies the desired properties, but that is again something that we would not cover in this class.